So I think most of you know me. I'm Kieran Connell, co-founder of the BitShifters Collective. We've made lots of demos for the BBC and games, and a lot of those demos involve lots of hacking of the CRTC registers. So I thought I would give you a presentation on what the registers are, what they do, and yeah, hopefully we'll learn something. As always, I'll start with a quick disclaimer. This is all somewhat simplified. There's lots and lots of information about all of this online. A new advanced user guide is always my source of truth, although there's errors in it, which is slightly annoying. The CRTC chip in the BBC is the 6845, not actually the Motorola, originally it was Hitachi. So the Wikipedia page is actually a great place to see the schematic, the pinout and more details as well. So let's start with why would we want to do this? Why would we want to hack around with the CRTC registers? And probably the most common thing that people want to do is to set up their own custom screen modes. And we've already seen that in some of the demos today. You want to change the screen dimensions, and this can save us some RAM. Obviously, a 20K screen buffer out of 32K is a big chunk, doesn't give us much left. Hardware scrolling with the CRTC means that we can move the screen around essentially for free. It's almost impossible for us to do software scrolling at any reasonable speed. It's just too expensive. And then later on, once you kind of get to know the registers, and if you can update the registers mid-frame, then you can start doing some more advanced effects. So things like vertical rupture. This is a term coined by the Amstrad CPC scene. Essentially a way of allowing us to address different parts of screen RAM and display that all in one frame. And then another thing that a lot of people want to do is smooth vertical scrolling, something like FireTrack. And you can do this in a few different ways, but again, vertical rupture is kind of a good way to do that. Not going to cover 3 and 4. I think those are sort of advanced effects and require understanding of interrupts and timing as well. I think we've got enough to cover today, just going through kind of 1 and 2. So let's start off with what the CRTC is responsible for, or more accurately, the 6845. And the 6845 on its own is not enough to generate our image, generate our screen display. So it actually works in parallel with the video EULA, Acorn's EULA chip. And the sort of division is split such that 6845 is a display controller, and the EULA is sort of known as the video processor, VidProc sometimes. So 6845, this is responsible for generating signals to control our raster display. So there's things like vertical sync, horizontal sync, and there's literally a pin on the chip with these signals on it, and that gets fed out to the display. The EULA, on the other hand, is actually responsible for generating the pixels. So a big distinction there. 6845 generates addresses that are timed to the raster. And so it outputs the address for the screen RAM that we want to be displayed as the raster is passing across the screen. But the EULA is responsible for actually reading those addresses from RAM, converting those bytes into pixels, which it transforms through the palette. Display controller also manages things like interlace, cursor, light pen. Not going to talk about interlace today. I'm going to pretend interlace doesn't exist. It just adds complication to things. And actually, for most of our purposes today, interlace doesn't really factor in. The EULA actually controls the clock speed of the 6845. So it can run at 1 megahertz. This would be kind of low frequency modes, so modes 4, 5, and 6, and or 2 megahertz, which is our high frequency modes. So mode 0, 1, 2, and 3. I'm not going to talk about mode 7 either. Mode 7 is kind of a special mode, and again, a bit of a hack. So it's probably worth us covering mode 7 and teletext in a separate session another time. EULA also controls the output pixel rates. So whether you get like narrow, small pixels in mode 0, or you get big, fat, chunky pixels in mode 2. And then to access these chips, the 6845 has 18 write-only registers, accessed through Sheila. But the EULA has just 1 write-only control register and then 64 bits of palette RAM. And again, access through Sheila, but at a different location. Now, we're not going to talk any more about the EULA. Again, I think there's enough interesting things to discuss with the EULA and enough sort of complexity that it would probably warrant a masterclass of its own. But if you, for the impatient, then there's a lot of great information on BeebWiki. I recommend you check it out. So really quick recap of what a raster display does. Like what signals do we need to send to the screen in order to generate a valid display? So, and we're talking about PAL here because we're BBC owners and in UK land. But for a PAL signal, we need to have a timing, a horizontal timing for our raster of 64 microseconds. And that means basically every 64 microseconds, we need to send some sort of horizontal sync pulse. And that gives us one scan line, one raster line. Again, pretending that interlace doesn't exist, for our full frame, we need to have 312 total scan lines. So that means every 312 scan lines, we need to send some sort of vertical sync. And if you do the maths, then 64 microseconds times 312 scan lines is 19,968 microseconds, which is actually 50.08 hertz. But again, it's because we're sort of ignoring interlace. If you have interlaced frames, then it comes out at 50 hertz, but we're not going to cover that. One thing that's probably quite important to start getting your head around is that the 6845 is primarily a character-based display controller. So it's originally designed to kind of be used with ROM chips that contains the characters in ROM. And so actually, for each scan line, it displays characters for some portion of the scan line. And a number of scan lines together make up a character row. But actually, within one character row, when the raster comes back around to the left of the screen, it actually resets the address that it's outputting. It outputs the same address for every scan line in the character row, which is a bit weird. But the way that the BBC is wired up for its addressing means that we have our familiar 8 bytes coming down on each scan line. And then we display a number of rows to make up our full screen. So let's just go through the 6845 registers in turn, just to have a look at them. So we start off with 4 horizontal registers. So the total, and I've got the units here on the right-hand side. So there's a total number of characters across the screen, but obviously only a portion of those are displayed. And then we also need to specify what the sync position is going to be. There's also a register which deals with what they call the horizontal sync width and the vertical sync time. Again, you probably want to leave those alone, leave those as defaults. Otherwise, yeah, you're unlikely to get a valid signal. Then there's a chunk of vertical registers. So again, the vertical total, the number of rows, the total number of rows on the screen. There's this register here, R5, total adjust, which is in scan lines. And we'll take a little look at what that can enable us to do later on. Again, not all of these rows are displayed. Normally, we only display 32 of them. And we need to also tell the chip when we want the vertical sync to be triggered. There's a set of control registers. So we've got interlace mode, display delay, cursor delay. There's also some cursor registers, so defining when the cursor starts and ends and how it blinks. But R9 is quite an important register. So this is the number of scan lines that make up a character row. And normally we have 8 scan lines in a character row, but it doesn't have to be the case. And again, I'll show you an example of what we can do with that. And then finally, we have some address registers. So probably the most important, R12 and R13, those are our display start address, and we'll use that for hardware scrolling later on. You'll notice that some of these registers, so R0, R4, R9, they've got this sort of -1 in brackets, and that's because the values that we put in those registers are actually 1 less than the value that we want. And simplifying greatly, this is because within the 6845, there's essentially a lot of counters that correspond to these registers. And the logic generally, these counters count up, and then at some point, they're tested for equality against these registers, and then the kind of state logic within the chip advances. And for whatever reason, it was easier and cheaper for this equality to be against the value -1 rather than the full value. So let's go back to our display and just put the registers on top of this. So these are our horizontal registers. So R0 here at the bottom, this is our horizontal total. R1 is the number of horizontally displayed characters, and R2 is our horizontal sync position. And then R9, we've just seen, is our scan lines per row, -1. And then we have our vertical registers. So the number of rows displayed, the vertical total, and again, sync position. And then we also have this little cheeky vertical total adjust in scan lines, which is a very handy feature of the 6845. And this allows us just to nudge the screen display by a single scan line at a time, which can be used and abused for that smooth vertical scrolling. So just taking a look again, but this time with the actual default values for modes 0, 1, and 2. So these are the high frequency modes. So horizontal total is 127, and that's because we want 128 characters across the full width of the screen. And this is because the chip is clocked at 2 megahertz. So for every clock, it's outputting a character. And so 128 characters, we can do 2 of those in a microsecond. So we have 64 microseconds for the width of the screen. So for the display characters, there's always 80 display characters in mode 0, 1, 2. Obviously, this doesn't, I'm not talking about the characters that you might see when you're typing. I'm talking about a character from the CRTC's point of view, which we know is 8 bytes. And then this horizontal sync position here is 98. So it's about 18 characters beyond the end of the displayed portion of the screen. We have 8 scan lines in our row. And then if you take your 312 scan lines divided by 8 scan lines per row, you get 39 rows in total. But R4 is one of those -1 registers, so R4 by default is 38. On the Beeb, we have 256 vertical resolution, so that's 32 rows. And normally the vertical sync position, depending on whether you're a B or a master, it's usually 35, 34, something like that. And then normally, but again, I'll show you when this is not the case, our vertical adjust is just 0. So programming the 6845 is very easy. The official way to do this is using VDU23 code 0. So just issue this VDU command with the register value, the register number and the value you want to set it to. Or you can poke this directly in BASIC. Just poke the Sheila addresses here, FE00 with the register number, FE01 with the value. And obviously you can just do this in assembler as well directly. You don't need to set any interrupts. But one thing that's important to note is that these register values take effect immediately. And this is why when you change mode, you might see like a resync or a bit of a glitch on your monitor. And it's because you're setting these register values in some particular order, but the counters that they correspond to might be at different values, and you might actually set the register value before or beyond the counter, and so actually it has to sort of wrap around before that logic takes effect again. And you can change mode without glitches, but it actually requires quite careful timing. You need to know where the raster is before you set them. Although they take effect immediately, and we'll talk about this a bit more when we get to hardware scrolling, the screen start address register is actually latched. And so although it's set immediately, it's actually only read at a very specific point in the 6845's logic, essentially at the beginning of each display cycle. Right, let's go on to a demo just to illustrate everything I've been talking about. In that, let's have a look at this. So I presume you can see this okay?
Yes.
Yeah, great. So let's just go through a few things that you might want to do with registers. This is just in BASIC. It's just poking the address values directly. You can't read them, so I've got an array here with the sort of defaults. I've got a just a little summation of the scan lines based on the register values, and also the amount of RAM that we're displaying. And it's just a little register browser that I put together. And if we get into trouble, then we can press R to reset. We're using JSBeeb here, has very accurate emulation of the 6845. I think BeebJIT and B2 are just as accurate. Some of the other emulators, maybe not so much. One thing to note, actually, JSBeeb is a little bit more forgiving than your actual Cub monitor. I did try this on real hardware, and it's very easy to get kind of screen roll and lots of flickering, but easier to demonstrate and safer to demonstrate in an emulator. So the first thing we might want to do is just reduce the amount of the number of lines that we're displaying in order to save some RAM. And so that's easy. We just reduce our 6 here. And I actually did this with Prince of Persia. I think we had 25 rows, and so we get under 16K there for the screen. It's nice. I mean, even a lot of 8-bit computers use 320 by 200 as a resolution, and that's what we have here. And there we go. We've saved 4K, which is a good chunk and quite handy. You notice, of course, the display is at the top of the screen. So if we want to center this, then we need to adjust the vertical sync position. And again, just to sort of help you think about your mental model of how the screen works, if we increase the sync position, then the screen moves up. And if we decrease the sync position, then the screen moves down. And this might sound a bit counterintuitive, but if you kind of think about how this works, every time you decrease the sync position, it means that this trigger for the raster to move back to the top of the screen happens earlier. But we still have to have our total 39 rows, and therefore more of those rows will appear at the top of the screen before we start the new display. And equally, if that sync position is greater, then the sync will be triggered later, and there are fewer lines to display at the top of the screen. And actually, we can see this if we go the other way and display too many lines, so we keep increasing this number. First of all, you'll see that the screen wraps around, and we'll talk a lot more about that in the hardware scrolling. But actually, you can go all the way up to 39 visible lines. You can see that 39th line has appeared right to the top of the screen now. Again, you can kind of adjust that. Kind of gives you a sense of there's always 39 lines making up the frame, but we only display a portion of them. And the sync position sort of determines when that gets reset to the top. Next thing you might want to do is reduce the horizontal resolution. And so here, if we go for this horizontal displayed, okay. First of all, you can see that the characters, the column numbers I have at the top, we're reducing this by 1 character, but of course, this is 4 pixels in mode 1. I should have made that clear at the start. This is a mode 1 screen. So you can see 1 character from the CRTC's point of view is 4 pixels here. But yeah, the screen all starts to skew, all the text starts to skew. And this is because as far as the 6845 is concerned, RAM is just contiguous, right? It has a number of characters that it displays in a single row. And when it comes to the next row, it just carries on through memory. It doesn't the actual layout of the screen is just entirely contiguous from its point of view. And you might remember this effect, this kind of screen wipe effect is what was used in Ghouls. It's a very simple effect by reducing that horizontal display, and you kind of get this screen wipe. What a lot of people like to do is just about see it here in the middle. R1 here is 64. And so this gives us 64 characters by 32 rows. And this is 16K, so this is a nice square screen. And also has the advantage that each character row is 2 pages, is 512 bytes. Again, if we want to center this, we'll need to change the horizontal sync position this time. The same thing here, if we want to move the screen right, we actually reduce that value so that the horizontal sync pulse is getting sent earlier. And so therefore there are more characters to display on the left-hand side. And we can kind of center it somewhere like that. So that's a nice 16K square mode 1 screen, quite a nice configuration. If we have a quick look at the total adjust, we can just move that screen down by sort of single scan lines here, which is like, this is quite interesting. And this is what Orlando noticed and took advantage of when he was putting together the smooth scrolling for FireTrack. You'll see that the sort of total number of scan lines here is now going away. It's diverging from 312. Now, it depends on how tolerant your TV is. At some point, it's not going to like this signal. If you want it to be a nice valid signal, then it needs to stay at 312. And we can kind of get away with this in an emulator, but at some point that's going to break on a real TV. So there are techniques we can do to take advantage of that register, but keep the total number of scan lines the same, which we'll hopefully cover in part 2. If we take a look at scan lines per row, so normally it's 8, but because this is a -1 register, the actual value is 7, but it doesn't have to be. So we can increase this, and then, okay, this suddenly starts to look like our mode 3 or mode 6 screen. And actually we can kind of change all these register values to be the same as mode 3. We can end up with a kind of mode 1 equivalent of mode 3. So we kind of get 4 colors, a bit like mode 6, but in 4 colors. And so if I remember rightly, there are 25 lines in the mode 3, mode 6 screen. And you can see that the total number of scan lines here is now a sort of whopping 351. This will probably be rolling like crazy on a real monitor. So we need to get our vertical total down. Oh, no, too far. And our vertical sync position as well. And then we kind of increase that again, because actually in mode 3, mode 6, there are 2 blank lines between each character row. So it's asking the 6845 to display 10 scan lines per character row, but actually only 8 of those have valid data, and the other 2 get blanked. So again, we can reduce this. I think R4 is 30. In mode 3. But you see the closest we can get here is 310 scan lines. So actually mode 3 does use vertical total adjust just to add those 2 extra scan lines on to give us that consistent 312 scan lines. So this is kind of a mode 1 equivalent of mode 3. So we've got 4 colors here using less than 16K, and we have these nice black spaces. You can also mess with the cursor if you wanted to do so. So you can have a nice block cursor if you wanted to, or you can actually have a weird top cursor, or you can have a middle cursor, all set with those registers. That's quite fun. And then the final thing, an example of reducing the scan lines per row below 8. So this is kind of the fortress approach. As we'll have a look at in a second, like when we're doing hardware scrolling, we can only change the address by sort of 1 character. And 1 character at the moment is 8 scan lines vertically. So if we wanted one way of doing scrolling by a smaller amount up and down is to reduce the scan lines per row. But again, we're going to have to adjust all of the other registers to compensate. So every time we reduce this, we end up with a smaller number of total scan lines, and we end up with this weird sort of shrunken screen. Again, this probably wouldn't display properly on a real TV. We can kind of increase this, and eventually we can end up with quite difficult to see, but we could end up with like a half-size screen. It's still using 20K. I think that's, yeah, 312 there, just about. But yeah, we have this now shrunken screen. We've got 4 scan lines for each character that we're displaying. The other 4 are kind of lost, but it does mean that if we were to display something within here, then we could scroll around it sort of 4 pixels vertically and 4 pixels horizontally. And that's kind of roughly what Fortress does under the hood to some extent. As that's kind of it, that's just a quick demo. I'll put a link to the basic program if you want to have a go yourself. But yeah, it's quite a nice way of exploring and experimenting with the registers. Yeah, probably used with caution on a real TV, but nice and easy in an emulator. Okay, so moving on to hardware scrolling. This is done through changing the display start address. So this is registers 12 and 13. Again, just remembering 6845 works on characters. So one character here is 8 bytes. And so therefore our CRTC character addresses are essentially RAM addresses div 8. And the address can be anywhere in the bottom 32K of the memory map. And so this means RAM up to 7FFF, and this corresponds to FFF for the CRTC address. Display start address, R12 is the high byte, R13 is the low byte. But as I said before, these values are latched, so they're only read at the start of a new display cycle. So essentially at that sort of top left corner of the screen. Normally you would only have one display cycle per display frame, but of course, if you change the registers in the middle of the display frame, then you can actually break this and you can have as many cycles as you want. And this is kind of this vertical rupture technique, which we'll talk about next time. So for hardware scrolling, just change that display start address each frame, easy. So we think about our high frequency modes again, 0, 1, 2. If you add 1 to the start address, it moves the display left by 1 character. And that's because we're starting the screen display 1 character to the right, so the whole screen appears to have shifted left. Other way around, if we subtract 1, then the display appears to move right. If we add 80, so that's the number of characters in our row, then the display appears to move up because we've started the display 1 row down, and conversely the other way. So this means for just writing a couple of registers, we can move the entire screen incredibly quickly, but it's very coarse. We can only do this 1 character at a time, or 1 character resolution. The observant among you will go, well, okay, what happens if you're changing this start address? What happens when the CRTC gets above 8,000? Because you said it can only address this kind of bottom 32K. There's actually wraparound logic that's on the BBC's boards that kicks in once you get above 8,000. And this is programmed by the addressable latch, which is a little bit fiddly, but the explanation of this is in the advanced user guide. There is an error in the table in the advanced user guide, but this is the correct table. Essentially, there are 4 values that we can set this latch to, and this affects the number that is subtracted from the address value. And these correspond to our different screen sizes. So we've got 16, 8, 20K, and 10K screens. And so when the address gets above 8,000, this number is subtracted, and it kind of wraps around back to these restart addresses. There's a whole load more information on address translation, which also does get quite detailed. Again, great information on BeebWiki. I guess the one subtle thing to note is that this address translation effectively, or sorry, this wraparound effectively only happens once. And so I'll move on to a quick demo of hardware scrolling. Oop, where we go? There we go. Okay, so this is another basic program, a little bit like the other one. We've got our, it's in mode 1 again, we've got our columns across the top, rows along the left. This time, just so we can see what's going on, I've added another set of columns on the bottom in red and rows on the right. And then if you can see it, there's just a little yellow dot and the very, very last byte in memory, so that's 7FFF. And here we're displaying the screen start address in RAM and what that corresponding CRTC address is, and also what the wrap address is based on the current settings. And so here we can just scroll around and you can see what the effect is. So if we add one to our address, that's obviously moving us 8 bytes in memory. We can scroll around a character at a time. And you'll see that the screen starts to wrap here. So we've got this yellow dot here, and then we've wrapped around back to 3000 there. And that's really all there is to it. If you want to not wrap around, then you need to figure out how to write your new data into this column on the right-hand side or on the left-hand side, so that if you want to do scrolling for your demo, like or your game, like Planetoid, then you need to be able to write that column of data in to the, that's what you'll see as the screen is shifted. And then similarly for up and down. So if we move down, we're just adding 80 or hex 50 here to the CRTC address, and that makes the screen move up. And then subtract it, and the screen will move down. But we don't have to stop with our 20K. We can actually go all the way down to the bottom of RAM. And this is actually quite a nice illustration of quite how much RAM the screen takes up. So we've only got, this is a 20K screen, and this is, we're now visualizing the bottom 12K of RAM here, and you can see the numbers, the values changing in Zero Page and in some of the OS workspace. And yeah, you can really see how much of that's, how much this, of the 32K our screen takes up. And when you visualize it that way, there's really not a lot left for making games. Hence, reducing the screen size is a really good way of getting some of that back. And then just a quick note on this kind of wraparound, just to try and help you visualize this. So I put a little thing in here. If I toggle these on, these little arrows just point to the memory addresses. So there's 3000 there, 4000, 5800, and 6000. And so if we move the screen, we can see that 3000 ends up somewhere here in the middle. And yeah, at this point, you sort of kind of realize that if you're doing hardware scrolling for your game, then your sprites can appear anywhere on the screen. At some point, they might end up being wrapped around this this endpoint. So your sprite plot routine is going to have to be able to cope with that and actually wrap the screen address when you're plotting. Otherwise, it's not going to be in the right place. This kind of help you visualize what happens when it wraps around. And actually, I can show you the different wrap values. So if we set our screen start address to 5800, and then if we set the wrap value to 5800, you can see that we just end up with effectively the same screen again, because when it got off the end here with our little yellow dots, it just came back around to 5800 and just displayed the same bit of memory again. Can also change that to 4000. Again, we kind of get this bit of memory that's displayed, sort of restarting, that was sort of somewhere in the middle of the screen. And then finally, you can kind of visualize what happens, why the wraparound, or when the wraparound only actually happens once. So if we set the wraparound value to be 6000, then when it comes to wraparound the second time, actually that doesn't happen. It actually goes back to zero. But most of the time you wouldn't encounter this, but it's just sort of helpful to see what happens in different circumstances with those wrap addresses. And I think that's about it. I think that's everything to cover this time. Again, I'll put a link to this little basic program just to help visualize hardware scrolling. Obviously a lot faster in assembler, and you have time to fill in those columns or those rows if you want to make hardware scrolling games. Hopefully that sort of helped explain a little bit sort of how the registers work and just sort of how to visualize what the CRTC is doing. And yeah. So do we have any questions?
Yeah, I've been looking forward to this, and to be honest, you've answered the few things that I've been struggling with, so I'm a very happy chappy, thank you.
I'm glad to hear it. And hopefully that's that register browser was actually quite fun to put together, and it's quite handy to just sort of mess around with the values. So try them on an emulator first before you then plug them into your cub, just in case.
Well, that's exactly it. I didn't have anything quite like what you've written there, but I did create a little program for messing with them, and I mostly figured it all out. But yeah, no, thanks. That was fantastic.
Yeah, that program is very attractive, Kieran. So thanks for offering to share that.
No problem.
I was thinking, Kieran, with your with your browser there, if you could set up something like the Shift key to either apply those values or to display it using the original values but without resetting them. So that, like when you're trying to set the 4 scanline high character, you could hold it down, tweak the values, let go, and it goes back to it. And equally, while you're trying to find the
yeah, that might be a nice idea. Just set the values and then apply them all at once.
I mean, so
it does get a little bit tricky to try and visualize things or see what's going on when you've got just a couple of scan lines per row.
Yeah.
Is it possible to scroll, say in mode 4, 2 pixels rather than a character row on sideways scrolling?
In which mode, sorry? If you're scrolling horizontally, then it's always going to be per character, and so you're essentially you're limited by the number of pixels in that character in 1 byte. So in mode 4, it's always going to be in multiples of 8 pixels.
Kieran, if the start address of the screen is changed and you do a clear screen, is that also changed then?
I mean, depends how you do a clear screen. I mean, the OS is going to keep all its. I mean, this is just poking the register directly, so it's not going to be respecting any of the OS's values. So it's probably not going to clear that screen for you properly. It's going to clear what it thinks.
So you have to clear it manually by with your own code.
Yeah. I forgot to mention, of course, that this is also the way that you would do double buffering. So you would just set the screen address to be something different between 2 different addresses that don't overlap.
One of the things I found out the hard way, again with some of your guys' help, was that you can mess with these registers, and it's all good and well if you're doing your own graphics routines, but it doesn't necessarily work well with BASIC if you're going to be using things like printtab. If memory serves me correct, on the BBC Model B, you can actually change the memory map, or there's a lookup table for the start addresses of each row. But on a BBC Master, it just doesn't seem to exist. Which
it's a good point.
My editor out.
Yeah, it's not so handy in BASIC. I guess you can probably reduce the number of rows, but particularly if you're doing something changing the horizontal number, then all of your kind of start of line addresses that BASIC assumes is going to be all completely wrong.
It's easy enough to make your own print tab. The graphics routines is a different thing entirely, but I've got a special use case there. I'll just have to rewrite it. It's fine.
Kieran, there are some questions in the chat you might want to pick up and clarify. I think from Bill Carr, if you scroll up, there's been quite a few
I think
messages.
Rob has been answering. So I know it's. I try and think always when I'm working with the 6845, just think in terms of characters. So and 1 character is 8 bytes, and it's just because that's the way the registers work. So normally you've got sort of 80 CRTC characters across the screen. They're 8 bytes each. So 1 character row is 640 bytes. which is then, but yes, if you're just adjusting the register values, then it's just 80. But yes, as Rob says, you can overscan quite far as well.
Yeah.
So you
Annoyingly, on
increase
two
the
of my
size of the screen. Go on, Tricky.
I was saying, annoyingly on two of my CRTs, it's 97. Or 96.5 anyway. So hence my Pac-Land demo is actually 97 characters wide, not 96. I think
Yeah, I think I've done that. I think 96.5 is the most I've got up to.
Yeah. I think the spec allows for more, but I like even just. So Kieran, I guess you're not going to address adjusting the sync pulse width, since it's not really well,
No,
supported on LCDs.
Yeah.
Which is-
First of all, I've never actually tried it, but and yeah, secondly, it doesn't work on LCDs. So
yeah, it was only
if you want to give a brief explanation, then go for it.
Okay. Well, you saw on Kieran's settings, you can set the width of the sync pulse, and it is definitely best not touched. But what a modern LCD does is it picks, I can't remember if it's the beginning or the end of the sync pulse, to decide that is the point in time when it happened. But on an old school CRT, there's a circuit that watches for it and effectively ends up picking the middle of that pulse. So if you change the width of that pulse, which is also measured in characters, if you make it one character narrower, the center only moves half a character. So effectively your horizontal sync position moves half a character, and you can scroll in half character chunks. There's apart from the major downside of it not working on LCDs, the other downside is it means that you actually have to clear 2 pixels off one end of the row and draw 2 on the other end if you don't want it to be visible, which is a pain in the bum. But it is supported by, I think, JSB, BM, and possibly BM now. I'm sure B2 does as well as PyTube Direct. And I think not PyTube Direct, Pi to RGB, RGB to HDMI using the Pi, and something else. Yes, FPGA Beep. I think they all support it, but obviously that still probably doesn't even get you halfway to coverage on as far as Beep users go. Yeah.
So I mentioned when you got cut off, actually, that when I was using these beams back in the day, back in the 90s, I had no idea about any of these things, and I remember just going, well, let's just throw a random chunk of numbers at it and see what happens. And well, it actually, my TV just gave up the ghost at that point. It started flickering and turned off, and then it wouldn't turn on. Or it would turn on, but there was no image. Now, I remember thinking, right, I'm never going to mess with this again. But I actually don't know if it's like physically possible for the for this chip to actually cause that level of damage on a TV. Ooh. Did that go through?
Yeah. The electrical guys on the forum say that it is possible, but probably only on a quite an early TV, 60s or 70s. Because the frequencies can get out of hand.
My first colour TV. Yes, I had loads of old equipment.
But yeah, I don't know about the electrical side of it.
Dominic Beasley's just commented, it's fine on real CRT so long as you adjust the other registers. You can also get 56 characters teletext. He's provided a link to Stardot.
Sorry, Dave, I was going to say teletext displays and teletext addressing is a whole other kettle of fish.
You were showing reducing the heights of the character cells. Did you say that data between the cells is lost then?
You can still use this, it just won't be displayed.
Yeah, it's not displayed. Right.
Yeah, yeah. But obviously it's, at that point you've got these little fragments of RAM. But I think Vortress does store some of the sprite data in there, if I recall correctly.
Cool. Yeah. No. So, is it possible to set the start row of so nudge the start row down by one as well to get like a vertical blind thing? No, it always starts at 0, does it? Yeah. Oh, well. That was an idea for something then.
I think that's talk number 4, isn't it, Kieran?
Oh, what, RBI?
Yeah.
Yeah, that's that's quite a hard one to explain. It is possible to address any line of data and display it on any line of the screen, but it requires like absolute single cycle register change precision. It's what Vectorize did for the Evil Influences demo, but yeah, it's you literally have to be cycle exact on the register changes for it to work.
And Rob Coleman's commented, there's an overscan demo on 8BS. I think it's the GLM PD disk 8. It messes directly with the OSVDU variables, so it doesn't work on the master. I'll just quickly, I think is it this one here by Lars Österballe? So it's GLM08 graphics 04. Does that?
Yeah, that's the one.
Yeah.
I think that's it. I think it's like the first one on that. It'll run like on a B, or I think maybe a B+, but not a master.
Okay, so anyone watching on the video, this is on 8bs.com, and you hit the catalog link and scroll down and you'll see it there.
Yeah, Lars did some quite crazy CRTC sort of just little ditty demos, like including he did some weird stuff with yeah, shifting the screen, shifting the horizontal sync position, kind of midline, mid-frame, to try and kind of do a wibble effect. But again, you kind of got to allow the screen some time to kind of settle if you want it to then have a straight portion. And very rarely works in emulators. It's not desperately predictable, but yeah, he's got some interesting effects that he messed around with back in the day. I don't know when they were written, actually, those demos.
One of my LCDs that changing the sync pulse width does move the sync, but not by what you'd expect. Like you increase it by a character, it moves it by about half or a quarter of a pixel. So you make it about 10 times too wide and it moves it a whole character, but then doesn't work on anything else. And it's non-linear as well.
I think that covers the basics on registers that you just sort of set and leave, or registers you might change per frame. But yeah, the more advanced stuff is changing registers mid-frame, which, yeah, we can cover next time.